This is Dr. Christy Patton-Lokes from Missouri S&T, and we're going to continue our discussion of how we can apply energy balances to some simple problems. So the basic process is going to be much the same as what we've been doing with material balances. We're going to start with a labeled diagram. We're going to show all our streams in and out. We're going to put a material table, but this time we're going to expand it to include energy information. When we get to some future classes, so like your design courses, we call this a stream summary table. So for each stream, we're going to list all the components and the total flow rate. We're also going to list the temperature, the pressure, and for a system with flow, enthalpy data. For a closed system, we'll list internal energy data. Then you're going to do a degrees of freedom table. So when you count how many equations you have, you'll need to add an entry for energy balances. And when you're looking for which variables you have, you may find that your unknowns might include things like temperature or how much heat is required to do this system. Now, you'll then write the mass balance, write the energy balance, and it may be that you find that you need to solve these simultaneously. Let's look at an example. So let's consider a waste heat boiler where combustion gases from a furnace are used to make saturated steam. So we've got some really hot waste material from a furnace, okay? We're going to send it into a waste heat boiler and use that to take water and turn it into saturated steam. So we want to assume that the gases are ideal gases. That's going to simplify our calculations. And so for the information shown in this table down below, we want to find the flow rate and the temperature of the steam that would be generated. In this particular case, the volumetric flow rate of the waste gas into the unit is 1,000 cubic meters per hour. So we're going to be adding some of those topics that we did in Unit D, such as using volumetric flow rate, so that we can find these other things. So what we have given is we have compositions of stream 1 and stream 2. Stream 1 is the feed material, the feed waste gas, and it's going to come out with the same composition. So 1 and 2 have the same composition and the same flow rate, F1. The temperature is going to come in at 600 degrees C, and it's going to leave the waste heat boiler at 200 degrees C. So we're going to deplete the energy from this gas stream so that it can be transferred to the water. Now the pressure for this waste gas is all at 1 bar. Then we have stream 3 and 4. Streams 3 and 4 are going to be water. And this is misplaced. Sorry about that. That's 1 right there. Okay. And so what happens is we've got water. It's water that comes in here and water comes out here. But the key thing is that we're going to transform it from a liquid at the feed to a gas at the exit, or a saturated vapor more properly. Now the flow rate will remain the same as long as I'm talking about gas or mole flow rate. I know the temperature of the water coming in, the liquid water coming in, but I'm going to try and solve for the temperature of the steam that leaves. And I know that the pressure in this case is 3 bars. So how are we going to solve this problem? Well, we're going to need data. So we can go to, and the page references are in the old hard copy book, but you can also find these in the appendix of the online textbook. And so what you'll find is on page 652, or on the ideal gas tables, there is a table that has enthalpy entries for ideal gases at various temperatures. And so at the feed temperature of 600 degrees C, this first column are the enthalpies that one finds. And at 200 degrees C, these are the enthalpies one finds. So the enthalpies have decreased across there. I did not look for water for those for the liquid phase because there was no water, so I didn't need to look that up. Don't look up extra stuff. And again, moving this down here where it belongs. I have liquid water coming in stream 3 and vapor water coming out stream 4. These are listed in per mass instead of per mole. And so to be consistent, I had done everything here in moles. So therefore I've converted these over so I could do it in moles. So I've taken the data out of the table and multiplied by the molecular mass so that I can get this in a per mole basis. So I've now gathered the data that is available in the tables. Next, well, we are told the volumetric flow rate of stream 1. We also know the pressure and temperature, so therefore I can use ideal gas law to solve for the molar flow rate of stream 1. I need to do an energy balance. Now the energy balance says that since this is an open system, delta H plus delta E kinetic plus delta E potential equals Q plus W. In order to have kinetic energy, one would assume that there was some movement, okay? So things physically moving with a velocity. And the way the problem is described, that's really not, there doesn't seem to be any significant velocity. So this is going to be essentially zero or no change over the course of the problem. Similarly, for potential energy, I'd have to have some sort of significant altitude change or some other form of change in a potential field. And in this particular case, that doesn't appear to be the case. And so the potential energy is zero. I'm going to skip next and come over to work. So work, if you look at work, work requires movement. And in this case, I just have a heater. Heaters just let material flow through them. They're very passive devices. There's no movement, so therefore there is no work. And we're going to find that this is going to be fairly common throughout our problems for this particular course. If there is work, it will be described to you with more detail. And then we have the heat transfer. So what about Q? The idea here is that I have some waste gas that's very hot, and I'm wanting to take cold water and then turn it into steam. And I'm going to take energy from this and transfer it to the water stream so that I have cool waste gas. Okay. Now, if this is my plan, would I not want to plan so that all of the heat goes directly from the waste stream to the water stream? So therefore, I would probably do my very best to insulate this so that no energy is wasted. And if I insulate it so that no energy is wasted, then Q would be zero. So this is a logical assumption, but it is not clearly stated. Now, earlier in the course, we mentioned that you should always list your assumptions. So these are the sorts of things that when I cross them off, they also give me an opportunity to remind myself that I'm assuming this. And then later, if I find out that that was a poor assumption, I can know where to come in and make that correction. So what I'm left with is that delta H, after all of this, is equal to 0. Now, delta H is going to be the difference between everything that comes in and everything that comes out. So that means that the sum of everything that came in will equal the sum of everything that comes out. In this particular case, what I have coming in are streams 1 and 3, and what I have coming out are streams 2 and 4. So I'm going to have stream 1 and its enthalpy, stream 3 and its enthalpy, and that should equal what comes out, stream 2 and its enthalpy, and stream 4 with its enthalpy. Now when I put the little hats on these H's, it's one way of designating that I know that this is has units of like kilojoules per kilogram. And I'm going to multiply by N1. Ooh, and I didn't mean kilogram, did I? This is per kilo or per mole. And this flow rate is going to be in like moles per hour in this particular instance. And so therefore my overall units will be kilojoules per hour for my equation. So this was just a little side, bar, trying to think through what the units are for this case. All right, well, I know the number of moles flowing in each stream, and I have enthalpy in kilojoules per mole for each stream, or joules per mole. You can work with either set of units. And so that's what I have done here. Now, unfortunately, I have in stream 1, I have CO2, I have all the various components. So this is what I've done, is I have all of my various feed streams. This is stream 1, and this is stream 3. This is stream 2, and this is stream 4. Okay? Now, when I look at this, I realize that I've only got one variable in there. It's an incredibly ugly equation, but I only have one variable, so I can solve for F3, which in this case turns out to be 13,260 moles per hour. Now I have already thought over here that my units all worked out, okay? So therefore I know that these units are good because I've checked that all the units are the same up there. And if this is F3, then I can turn that into a mass flow rate using molecular weights, and this has a flow rate of 239 kilograms per hour. So this completes this example. In future lessons, we're going to be looking at how one could gather some of this data when you don't have a data table handy. So where does this data come from, and how can we make approximations?